Hello everyone, my name is Sohrab, and in this presentation I will be talking about a part of my research that mostly deals with the data analysis part of landslides monitoring. During this talk I will touch on different ways of pre-processing instrumentation readings and weighting the impact of each technique from practical perspective. There are numerous slopes experiencing slow movements for which stabilization is not a feasible option since they are either not cost-effective or eco-friendly. As a result, proactive monitoring has been adopted as a reliable approach to cope with these hazards. Early warning systems have been developed based on this logic to assist engineering communities, authorities, or stakeholders to mitigate financial losses and casualties. On the right, you see a simplified chain of components in such systems. The readings of in-situ instruments or remote sensing techniques, which are usually in the form of displacements, are fed into the system, and using these values, velocity and acceleration of landslide-prone area will be calculated. Those will be then constantly compared against preset thresholds to raise appropriate warnings and alarms if they are violated. In such cases, when the system identifies the onset of acceleration or an imminent failure, corresponding protocols will be initiated. However, the raw readings are obscured by a scatter, which leads to calculation of velocity and acceleration values that are not necessarily a true reflective of ground kinematics. There are different filters devised for this purpose, with the main goal of separating the true trend of displacement from scatter. Having said these, our understanding on the performance of these filters and how they might potentially affect the integrity of an early warning system is inadequate. The study today that I'm going to talk about pursued this objective. My question was, what is the appropriate filter? To answer this question, we should first establish our criteria of defining a good filter. A suitable filter should yield displacements, velocity, and acceleration with minimum distortion, or in other words, with the least possible error. It also should be capable of identifying the onset of acceleration timely, and forecasting failure time by its process data should be as accurate as possible. To address all these items, we use a numerical analysis on a synthetic database and actual cases. Figure 2 shows a piece of horizontal displacement data that a geocube installed on the 10-mile landslide had reported with the frequency of 60 seconds. It is seen that small fluctuations in displacement diagram results in a cloud of points in velocity diagram, although our engineering intuition expects otherwise, saying that the velocity should be somewhat constant. Filters help us to automate this process with no personal judgment. It is a common practice to use simple moving average or SMA as the filter for this purpose. You can see its mathematical formulation here. At each time step, SMA simply takes the average of a number of surrounding points as the filtered value. The number of points considered in the filtration process are referred to as window size or bandwidth. On the right, black points are the filtered values of the data from previous diagram in the last slide. This shows that SMA has been rather successful to present results that match with our expectations, and for several years now, SMA has been the single candidate to deliver this task because it's very easy to understand and implement. However, disadvantages of this filter have not been really discussed so much, especially in comparison with other existing filters. The next filter is Gaussian weighted moving average, which is a modified version of SMA. In this filter, different points contribute to the filtered value differently. Now compare it to SMA that assumes a reading from 4 days ago, as an example, has the same significance as the readings from a few minutes ago. Gaussian filter, on the other hand, gives less significance to those that are temporally distant from the point of interest. The next filter also was Savitzky-Golay, or SG. This filter also works on a window basis, but fits a polynomial curve on the points in the window and compute the filtered value using this fitted curve. As I mentioned before, one of our methods to reach answer was numerical analysis on a synthetic database. We developed a comprehensive mathematical framework which I will not delve into today, but the gist of this method is generating a series of known curves that would resemble the displacements or velocity trend of a landslide and make them simulate a raw readings from an instrument. In figure 6a, you can see a few of these curves that we call them scenario. In figure 6b, the process of generating a scatter and unfiltered results are also presented. The perk of this method is that we're completely aware of the true value, which makes us capable of quantifying the error and judge the performance of filters objectively. Before applying filters to these unfiltered scenarios, it was essential to recognize how this process would fit in the real-time monitoring situation, which is the case of our early warning systems. Filters that I presented to you in the last few slides work on a window basis, and these windows are usually symmetric, meaning that equal numbers of data points from past and future are included in the filtration process. This might be true for post-processing purposes, but in real time we only have past observations, and therefore the window should be non-symmetric. Figure 7 shows examples of non-symmetric and symmetric types of window. A sample of results are shown here. Before talking about these diagrams, I'd like to note that the bandwidth ratio, or BR, is just simply a normalized representation of window size, and its higher value stands for more intensive filtration. Figure 8 shows how these filters behave when being applied to a scenario with major peak. This type of trend is common in velocity diagrams of landslides that undergo an episode of acceleration followed by a deceleration. The far left diagram is the SMA results, and different curves correspond to different filtration window sizes along with the true trend. It shows that when filtration becomes more intensive, SMA tends to attenuate the peak value and also procrastinates it to a subsequent time. We repeated this for all three filters at different window sizes to see how these observations would change in other situations. Figure 8b displays the peak position, and it shows that SMA is prone to procrastinate the peak almost 4 to 5 times more than Gaussian and SG filters. Figure 8c also accentuates another downside of SMA, since it shows that this filter attenuates the peak value at least 2 times more than other filters. Aside from these type of particular studies on single scenarios, the error was also quantified in different situations. Figure 9 is a sample of error calculation which shows that SMA with the highest error, while other filters have been more accurate and showing lower amount of error. These diagrams, in addition to many more experiments we performed, clearly emphasize the limitations of SMA. More studies in different filter application situations made us realize that the issue of lagged response is more deep-rooted and goes back to the non-symmetric window type. In other words, the nature of real-time monitoring induces an artificial lagged response in filters' performance. Figure 10 is an example of this phenomena, in which thin black line belongs to SMA results showing a significant shift, while thick and dashed black lines that represent Gaussian and SG filter results are showing much less lag. This can be seriously detrimental to the integrity of an early warning system if movement characteristics are not captured at the right time. We developed a method inspired by signal processing tricks to quantify the filter's lag. Figure 11 presents a chart that can be used to reduce the shift very efficiently. Although this chart provides a range of shift rather than proposing a deterministic value, it shows Gaussian filter is more reliable when it comes to correction of lag, which foreshadows the necessity of using SMA alternatives. One of the actual slides that we used for further validation of results was 10 Mile landslide. In southwestern of British Columbia, it is located in the Fraser River Valley 10 km north of town of Lillooet. Its movement is vital to a section of Highway 99 and CN Railway, and various methods and techniques have been employed to control and monitor its displacements. In this study, We used the GeoCube's data that recorded its movements for almost 2 years, and in figure 12b you can see the distribution of these units on this landslide. Filters were then applied to the displacement values, and these 3 diagrams show processed values at different filtration window sizes. It shows that increasing window size aggravates the lagged response of SMA, while Gaussian and SG are not impacted that much. For comparison purposes only, the inset on top right features also one of the scenarios from synthetic database that resembles the trend of 10-mile landslide displacements. The velocity diagrams were then obtained using the filter displacement values. Here, figure 14 shows a sample of results after application of SMA and Gaussian filter. The first row of diagrams belong to SMA displays that if this filter is highly sensitive to window size, and valuable information on landslides kinematics might be lost in the filtration process, while the Gaussian filter on the second row of diagrams acts more preservative on the trend while efficiently and effectively reducing the scatter. In the next step of the study, we investigated how filter selection may affect capturing acceleration moment and also forecasts on failure time. Figure 15 shows a synthetic scenario on the left with the known moment of acceleration and illustrates a synthetic scenario on the right that was generated using the inverse velocity method to see how failure time would be forecasted as a result of filters application. Figure 16 shows SMA would reach a 90% reliability in capturing acceleration moment 4 and 23 times later than Gaussian and SG filters. The failure time forecasts also underline rather similar conclusions. On figure 17 you can see that Gaussian and SG filters outperform SMA by 60 to 100% improvement in terms of accuracy of forecast on failure time. 17 datasets of failed case histories were also gathered from literature, and these filters were applied to them. It was again observed that SMA alternatives, Gaussian and SG filters, perform failure time forecasts much better than SMA, with the same 60 to 100% improvement in results. First part of this study is in the final publication stages, so if you're interested, keep an eye on the Journal of Natural Hazards and Earth System Sciences. I was also lucky enough to present part of it in GeoNiagara last year, and finally the last part of this study is now under review for possible journal publication. Thank you very much for your attention. I'd be more than happy to answer any questions that you might have.